Okay, and then in terms, this is a planning versus dyna, which is regarding how you are using the model function, dynamics model. And then this was about the pseudocode regarding the dyna version of actor critic, which is exactly the same as actor critic, except that you are generating the data using dyna. So this should have been straightforward. Visual representations, DQN is not able to handle continuous actions, but QTOB is due to their neural network formulation. We can modify the CNN used in DQN to train a visual dynamics model. And the answer is yes. We should modify this DQN network for discrete actions so that we regress like future frame per action. This is definitely possible. This, as mentioned, is not able to handle continuous actions, but for discrete actions, this is definitely possible. This is more like learning, if there are like 4 actions, learning 4 different neural networks, CNN, to regress future frames. So this is pretty much it, and we have a total of 110 points, and yeah, any questions? I mean, this was pretty straightforward in my opinion. You might have run out of your time. That probably was my only concern. But if you knew everything, you can, address everything well within the amount of time. So one question from Abhinav. Abhinav mentioned Monte Carlo instead of reinforcement. Reinforce, would that be fine? I am assuming that's the question for the 6.3. And the answer is you can kind of say that this is actor Monte Carlo. You are using Monte Carlo for your critic. You can get probably partial credit, but this should have been obvious that this is reinforced. So you'll get partial credit, yeah. Do you know when, the question from Nicholas, do you know when we'll receive grades? So the scoring of the midterm exam will be provided probably by the end of the week or like within a week. So the exam scores will be released. The final grades will be, of course, after your final project submission. Any other questions? And of course, you can come back to me after the grades are out. You can come to the office hour to check your exam and everything. Okay, when will we receive grades for programming assignment number 1? Jongwoo, you already have this, right?
I guess end of this week, like by Friday.
So yeah, Jongwoo just has to like fine tune it slightly. Jongwoo already has it. Yeah. Okay, that is pretty much it. And let us go back to our technical material today. Okay, I was initially planning to talk about decision transformers, but I kind of thought that it's a bit too early in some sense. It will confuse you. So I decided to cover an easier topic first, which was what we were planning to cover in any case, the evolutionary strategies. This is directly relevant to the policy gradient, which is your programming assignment number 2, and which you should be familiar by now through your midterm. So, what do we mean by evolutionary strategies? This is about robot action policy learning. So evolutionary strategy is about, a generic algorithm. However, we are particularly talking about using evolutionary strategies for robot action policy learning. It is a black box optimizer, and we have this funny slide, kind of compare, essentially a metaphor, comparing that we are running on evolution, where each animal you see over here is more like your policy. We will have a kind of environment where your bad policy will die and where your good policy will survive. And this will be repeated multiple times. And that's pretty much the spirit of evolutionary strategies. This is definitely different from optimization using differentiation, and we'll talk about it. So as mentioned, this is quite similar to the, I mean, what we are doing is trying to optimize, trying to obtain the optimal policy. And if I remind you how we were doing this in policy gradient, well, we always had a policy governed by a certain function, I mean, certain parameters, theta. And we defined the objective function, which was nothing but expectation of the future cumulative reward. And we said that we are able to do that based on the sample, which is the core of reinforce. And then what did we do? We tried to compute. I mean, this was the key. We would try to compute the partial derivative, essentially the gradient with respect to this target function, objective function. And then we did multiple rounds of enumeration, and finally we were able to formulate the equation as the parameter update rule. I mean, parameter update. And this was what you typically did in order to obtain the optimal set of parameters for your policy network. Here, we also try to obtain the optimal parameters for your policy network. However, we don't compute partial derivative like this. We do this in completely different fashion using evolutionary strategies. So the limitation of the policy gradient, for example, is sometimes computing the gradient allows you to stop, makes you to stop at local optimum. So you have a reasonable kind of policy that is definitely better than the random policy, but it may actually stop at local optimum, and it may never improve as your gradients will become zero at your local optimum. So you can easily get stuck. And there are tricks to avoid this, but this can naturally happen. I mean, this can inherently happen. So what's happening in such scenario? So let us imagine your objective function looks like this. What I mean by looks like this is, let us assume that this axis is your target or your objective function value. So you want to kind of minimize the objective function or maximize the objective function. I mean, depends on your setting. But given an objective function that has this distribution, and this axis here, these two axes here, just consider that as your neural network parameter. So this is a very straightforward case, simplified case, where your policy is determined based on only two parameters. So you just need to set two parameters right, so that this axis, the value in this axis, is minimized or maximized, depending on how you set this one. And if you actually look at how the policy gradient will work, well, you will be computing the gradient of these two parameters. So these two parameters are all the parameters that decide the policy. So you are computing the gradients with respect to these two parameters. And regardless whether you are computing the minimum or maximum, if your the objective function look like this, yeah, you are very likely to get stuck in local minimum or local maximum. So policy gradient, if your objective function looks like this, will just suffer. We need a different way of obtaining your optimal parameters in this case. So this is another kind of example. So let us just assume that the color is your objective function value. And let's say that you are maximizing your objective function, which was the typical setting in your policy gradient as well. And these two axes, this x-axis and y-axis I'm illustrating here, are two parameters solely deciding your policy. And under this situation, what you need to do is to get to this maximum. You want to optimize your x and y, your parameters, so that you go to the maximum. And if things look like this, and if things look like this, you are very likely to stop at local maxima if you just run gradient descent. I mean, the policy gradient, for example. So what should we do? So yeah, So your objective function is a function of your neural network parameters, x and y. And this is what you are maximizing, and this is what you have the control over. Changing this means changing your policy. I mean, it's essentially like changing your neural network. So I just want to set up, what I'm doing here is just setting up the problem so that everybody can visually understand what happens. And then let me also cover the background in terms of the genetic algorithm. How many of you are actually familiar with genetic algorithm? Can you raise your hand remotely? Okay, yes. Avi, I know that you're familiar with the evolutionary algorithm, but anyone else who's familiar with evolutionary algorithms or genetic algorithm? No one? Seriously? Kansana, okay. Anyone else? I mean, okay. Last year, when I was teaching it, I had at least like 5, 6 people who were familiar with it. Huh. So, okay, it seems evolutionary algorithms are being less and less popular. Okay, interesting. Okay, so let me try to give you a very brief background in evolutionary strategies. And this is the most vanilla case, the basic case of the evolutionary strategies, which is sometimes called a genetic algorithm. And the genetic algorithm is extremely simple. Although it looks complicated if we illustrate it this way, the main idea is very simple. We always maintain a population. What do we mean by your population? In terms of this policy, action policy running, a population means a set of individuals where each individual is a different policy. And genetic algorithm constantly modifies this population by selecting two parents out of this population, creating a children new policy out of these two parent policies, and then modify the policy like a mutation, and then try to evaluate how much this children, the new policy is suitable, how much what's the objective function with this particular individual policy, and then tries to update the population and then sometimes kill the population and so on. So to give you more details, population is a pool of individuals, a pool of policies. An individual gene. So each individual in evolutionary algorithm is represented with a gene. What do we mean by a gene? It could be like a bit string, or it could be like a real number. So each individual could be some bit string, or each individual could be some real number, or each individual, importantly, could be like a vector. So it could actually be a set of anything. I mean, if we set each individual to be a vector, that means that each individual can be the entire neural network parameters we are optimizing. So each individual is some set of parameters, we can say. And we have many of them, meaning that we maintain multiple individuals. And we always try to create a new individual, new policy. How do we do that? We sometimes select, I mean, this depends on what you do, but often you can select two parents out of the population. So you take two individuals at random or based on fitness. So each individual, if it's a policy, you know how good the policy is. You can simply run the policy and try to get the reward, and then it will give us the objective function, expected reward. So we know essentially the fitness or the score corresponding to each individual, and we can try to choose two good individuals as parents, two promising policies. And then, as mentioned, it's the fitness is the evaluation of the individual, which could be like the cumulative reward. And after that, we can try to generate the new children out of such, parent individuals. How do we do that? There are multiple operators such as mutation and crossover. What we mean by your mutation is we can select one of the parents and then try to just modify it